Good morning, everyone. So let's get started here. If you are attending online, I do ask that you turn your cameras on. All right, so just a quick comment about the midterm exam we had last class period. So there's one student that's gonna take the makeup exam today. And after that, I will be able to finalize all the grading and share with you your grades and feedback on that as well. And we're going to be talking in more detail um, about the exam on Monday, just so you know. All right, so for today, if you remember let's see, was it last Monday, I believe, we finished the lecture on the soil electroconductivity. And then at the end of that class, I asked you already to download the new data set in PowerShell script, create the 09 soil EC project with the subfolders, and then move the code and the data into the proper subfolders as well, and create the rproj for this. So I'm assuming you all have done this step already. So if you have not yet, you can go ahead and just launch this project for the R project icon for this, and we're going to start working with that. I'm just going to launch here my PowerShell script as well. Make sure you do that on your side, and let's start working on this. All right, so in lecture, we talked about having three different methods of collecting soil EC data in situ, where one of those was electrical resistivity, which is what the commercial example of that was Veris, right? So Veris uses electrical resistivity to assess soil electroconductivity on the go. And so this data set that we're going to be exploring today is one data set coming out of a Veris machine. So in this class, we're not going to see that in action, but we're going to work with the data coming out of that machine and how we would process that data. So if you start here on our learning objectives today, is going to be to import soil apparent electrical conductivity data interpolated for two different depths, and then export that to file. And just to kind of place us into the larger vision here again, this is going to be the last piece of spatial information that we're going to process before we actually create zones with them. So, just to remind you, what we've been doing is we're bringing in a raw data set, we clean it, we interpolate, we do the interpolation of it using IDW, and we export to file in a way that in the next step here, we're basically going to bring all of those process layers into the same script and then start making zones and validating those zones as well. So this is the last part of that part of the exercise. I left you here all the packages. I would imagine you have all of them already by this point, so just go ahead and run the chunk. I'm also setting this my theme map, which is just making some selections of what I want our plots to look like and just assigning that to an object. Then we can just call this object whenever we're making a plot, and we'll already represent all these changes here. So make sure you run that so we have this my theme object in your environment. And then as always, we're going to start off by just reading this data set. So the data set is a CSV file. Because of that, we're going to be using read CSV. So just go ahead and start typing that. It should be inside of your data folder. So in the quotation marks, we get out of the data folder. I'm sorry, get out of the code folder first, and then go in the data folder and just bring that soil-ec.csv. If you read that in, and we just print it very quickly here just to look at what is going on. So this was the output that this file came as. So what we're seeing here is that we have 8,000, almost 8,400 rows, where each row here would be a point on the field where it measured EC and then took that GPS coordinate to attach that value to. And as you can see here, these column headings are really not that useful, right? It's like F1, F2, 3, 4, 5, and ID. So they're really not very informative, I guess. But you know, we know here that F1 and F2 are the coordinates. And then just from working with this type of data here, F3 and F4 would be the soil electrical conductivity at different depths, at 2 different depths. If you remember, the soil various equipment most commonly have 1 or 2 emitting discs, and then 2 or 4 receiving discs that are at different distances from the emitting disc. And the farther away that the receiving disc is from the emitting disc, the deeper soil depth that signal integrates. And so that's why we have these 2 different depths here. So F3 and F4 would be so F3, the shallow, F4, the deep. And then F5 here is elevation, and this is in feet. So every time that we're taking a soil electrical conductivity measurement here, it's also using that GPS signal to associate with elevation data of that point as well. All right, so let's just think through this. I think, you know, some of these steps here, we work actual questions on the exam. So maybe I'm going to be asking some people that have not answered too many questions throughout the semester yet. Remember that this counts as your participation as well. So here, let's do all the wrangling in this next chunk. So we're going to start off with the object that we imported above called ECA. Let's give it a pipe. The first thing I want to give it is here, the next is just a clean names. In this case here, maybe it wouldn't be extremely necessary, but I like having that as a default task here just to make our names more straightforward. So let's apply clean names. If we just printed, basically in this case, just made everything lowercase. The next step here is I want to use a select to select some of these columns and also rename on the same step. So let's call here dplyr : select. As I was telling you here, so the F1 and F2 columns are the coordinates. So F1 is the X coordinate. So we're going to say, so the way, if you recall, the way we do this is we first say the name of what we want to be the new name of the column, and then we say equals to in the current name. So I would say if I want to rename this select and rename it to X, I should say X equals F1, not the other way around. We're going to do the same for the Y. So we're going to say Y equals F2, as that Y coordinate is on the F2 column. Give it a comma. As I was telling you here, F3 and F4 are the actual electrical conductivity at F3 at a shallow depth and F4 at a deep depth. And what these, at least from, you know, the way that the manual for Various explains this is that they assume F3, or I'm sorry, they assume the shallow depth to be integrating signal from 0 to 30 centimeters, and then the deep to be integrating from 0 to 90 centimeters. Of course, you know, this is not a precise measure, it's just an estimation, because as you would imagine, the depth which the signal is being integrated over will depend on other things. But as a rule of thumb, we assume shallow to be 0.30, deep to be 0.90. So what I want to call this next is ECA 30 to being the shallow one, underscore DSM. Remember, I always suggest that we include, first that we have column names that are informative. So right now, F1 through F5 are not, but also whenever we're making our column names, that we include the unit there, just to make sure that this is something very clear to whoever is using this afterwards, including yourselves. So now DSM here is the unit of decisiemens per meter. I just want to say ECA 30 underscore DSM equals to F3. And then the same thing for the deep one. So ECA 90 underscore DSM equals F4. And then lastly, the elevation column, which is F5. I want to call that 11 underscore FT for feet equals to F5. So if you run that, now you should be looking at something that looks like this. All right, so is this object geospatial in the sense of is this already a geospatial object? It's not, right?
Question.
Yes.
On the EC 30 and 90, what did you say the DSM stood for?
So DS is decisiemens per meter.
Okay.
Yeah. All right, so this is not a geospatial object yet, right? We have geospatial information in it that we can use to turn it into a geospatial object, but it's not geospatial yet. So let's go ahead and turn it into geospatial. So let's add a pipe. And what is the function that we need here? Let me ask Hejimar, what do you think?
SF underscore ASSF.
Yes, right. So it would be the function st underscore s underscore sf, right? So this is the function that we're always going to use to turn any type of object into an SF object. In this case here, we're using SF objects to represent geospatial vector data. Thanks, Hejimar. All right, so as if you recall, we have to specify where the spatial columns are. So it has this argument for chords, where we just need to use the C function to give it two values. The first one is the X column, the second one is the Y column. And just to remind you, I'm saying X and Y here because those are the names of the columns. If the columns were named longitude and latitude, that's what you would say there. All right, so if we run this and we print it, now it is a geospatial object of type point. However, it does not have a CRS yet. So let me ask someone else here, what is the function that we need to assign the native CRS here? Let's see, Dalton, what do you think?
Need to put in the 4326. Can't remember the function. It's just set STCRS underscore CRS.
Yeah, something like that, right? So the function would be st underscore set underscore CRS, right? So this is the function again. Remember this distinction here. So we first transform into geospatial object. Now we're setting the native CRS, which is not the one that we want it to be, but is the one that the data was measured under, right? So this is not what you wish it would be. This is what it was. It was at the time of data collection. So it has this argument value here. We know that this CRS is WGS84. I mean, I know it is WGS84, but if you did not know, you can kind of guess. Oops. You can kind of guess it based on the actual numbers, right? So this here, it is WGS84, which the EPSG code for that is 4326. Right, so if we run this and we print it, now it is WGS84. However, we're going to be interpolating here. And as we've talked a few times already about this, and we saw an example in class of what are the potential implications of that, we want to have this in a meter CRS instead of a degree CRS. So going from geographic to projected, we need one more function here. Let's see, Rolando, what do you think we should use here?
No, sir, I don't know.
That's fine. Let's see, can someone else, maybe here in Athens, help us here? What function do we need? ST transform, right? So ST transform is the function we need to transform a CRS. So once you assign the native CRS of the layer, then you can transform it to whatever you want using ST transform. And the value we're using here is 6345. All right, so if we run this, then print it, now it should be an SF object of type of geometry type point with a projected CRS that in this case is UTM zone 16 north. All right, so this is basically what we, the wrangling steps here. Now with every exercise we do, regardless of the type of data, we always have to visualize it using plots, right? So one common mistake here that I've made many times, and I'm sure you will run into at some point as well, is maybe, you know, if these columns here are not named X and Y, but they're named like longitude and latitude, sometimes I get confused and I say that, you know, so longitude is the X, latitude is the Y. Sometimes I flip them by mistake. And if you never plot this, if you never make a map of it, you're never going to realize that you made a mistake here. And you may continue your analysis using the wrong configuration, spatial configuration of this data. So if you invert these values here, probably your field's going to end up somewhere in Antarctica, which I'm sure it's not what you want. So
Dr. Bastos,
yes.
can you repeat this part? So when we have these STSSF chords, the next code, it says ST set CRS. I really got lost over there. Can you explain that
Yeah.
transition
So-
between STSF and CRS, please?
Yeah, so this step here, this first step, we are basically transfer. So STSSF basically takes what originally was just a data frame. So if we stop here, this would be a data frame. It's a tibble, it's a data frame, right? So right now, even though you can make a plot where you say X equals X, Y equals Y, it's going to look like a map, but it's actually not an actual geospatial object. So for us to transform this from a data frame to a geospatial object in R, we use this function here, STSSF, that requires you to tell what column on the current data set is the X coordinate, which column has the Y coordinate. We say X and Y here because those are the names of the columns. If the columns were named something else, maybe longitude and latitude, that's what you would say there, right? So that's what this function does. The next one here is just assigning the native CRS of this layer when it was collected, which was using WGS84, and that's the EPSG code for that. And the last one is just transforming that from WGS84 to UTM. And we do that because WGS84 is geographic projection. Or a geographic CRS where the unit is in degrees, and we want the unit to be in meters to be projected so we can do distance-based operations. So that's what we do with ST transform. So for example, it would be wrong for us to come here and say ST set CRS 6345. This would be wrong because the layer as it came to us was not collected using that CRS. So it would be wrong to do this. We first have to assign what natively was used, which is 4326, and then transform to whatever one we wish. All right, so coming back to the plot here, let's make a map of this. So I'm just gonna plug this data set that we wrangled right into a ggplot. As a reminder here, we use pipes outside of ggplot. When you get inside ggplot, you use the plus sign to add more functions. So, okay, if I want to make a map, and with the knowledge that this object now is an SF object, is a simple feature collection, what geom do I need here? Let's see. Let me ask Clint, what do you think?
Would it be SF?
Yes, that's correct. So we would use.
Like that, SF.
Yes, thanks, Clint. So geom SF, right? Because again, this is an SF object. If you print, one thing to notice is if we print this SF object, those columns X and Y are not available as part of the columns anymore. They were incorporated into the geometry column, so they are now embedded into this geometry column. So even if I wanted to say geom point and say X coordinate on the plot being equal to the X column, once we transform that to an SF object, you don't have that option anymore, right? You don't have that X and Y columns available for you to specify on any geom. So we have to use geom SF, which makes use of the geometry column here. All right, so the only thing we're going to change here is going to be the color of the points. Well, I guess if we just run, let's maybe run it just to see what would happen if we run it as is now. This is what it will look like. So to begin with, it looks like the shape of our plot of our field that we'll be working with. So, you know, we appropriately specify the X and Y here. Just, you know, let me just do a change here just to show you, and you don't have to do on your side. But if you know, here is very clear that X is X and Y is Y because we rename the columns that way. But sometimes the columns are named longitude and latitude, and perhaps, you know, sometimes I get confused myself. I say that one is the other when I'm specifying here. So what would happen if I actually say the wrong coordinates, the wrong order of the coordinates here? So let me run that and let's make this plot. So first off is looking very different from the shape that you would expect for this field. And also if you were to bring a base map behind here, or if you would show this in map view, you would be able to see the base map satellite behind it. You would see that you're probably somewhere in Antarctica if you missed the order of the coordinates. All right, so let me just give the proper order again and rerun it so we can proceed. All right. So I do want to color the points here according to, so let's say this plot here is the shallow one. So I want to say a yes color equals to, and then the column name that we have, I'm just going to print ECAW here again so we can see. The column name is ECA30_DSM. If we run that, so it does the color for us. I do, however, want to decrease the size of the points because right now they're overlapping a lot. So if we get outside of a yes, I just want to say size equals to 0.5. So now we can really see the paths, right, of this equipment here. So so various is something that can be dragged behind a tractor, maybe an RTV, maybe a truck. But it's just dragged over the field in passes. So we can really see those passes very clear in this map. I do want to make two changes here. One of them is to change the color scheme that we're using. Let's use a colorblind safe scale here. So I want to add a plus and call scale _ color _ Viridis B for bind. So if you run that, now we get this map here. And lastly, I just want to apply the theme that we created in one of the first chunks. The name of that object that carries all of our selections is mytheme_map. Just going to say plus mytheme_map. All right. This is what this plot looks like, or the apparent electroconductivity of the soil at the shallow depth looks like. Let me see something here very quickly. Okay, so if we just think about it, so the shallow depth, this would be from about 0 to 30 centimeters. This is what we're seeing here. Can someone help me to interpret this plot, this map, and understand at least what we're visually seeing on this data? Ushwal, can you help me here?
So we can see the distribution of soil EC with the green and yellow zones with higher EC, and dark blue or purple zone with lower EC.
Mm-hmm. Okay.
So,
Just let me repeat that for the people online in case they couldn't hear. So Ujjwal saying here that we're seeing distribution, the spatial distribution of shallow EC with yellow and green being higher values and purple and blue being the lower values. All right. You're gonna say something else?
I was just about to say like what's the application based insight we can get from the EC that maybe the area with higher EC are saline with more like water, maybe clay.
Okay, so Ujjwal was making the connection between the variables that impact EC as far as salinity, texture, and water. Now, let me ask someone else here. Let me go to Sandesh. So if we assume here for this map that EC is being controlled by texture, how would you interpret what you're seeing here?
Well, the clay soil has a higher EC as compared to the silt and the sand, and the yellow zone will be more to be the clay soils, and the lower zone for dark purple will be the more sandy soils.
Perfect. So Sandesh was saying, in case, I don't know if online you were able to hear, but he was saying that if we assume that this is controlled by texture, then more clay is gonna have more electroconductivity. So the areas that we see here in yellow and green would probably have more clay relative to the areas that we see in purple and blue, which probably have more sand, right? Yes, so that's how I would interpret that. Thanks, guys. All right, so really, if you just, yes,
Question. This is, more just kind of, I guess, a question of them actually like dragging the Veris rig across the field, but to me, it looks like they used like the same AB lines as they would have like planted with across the field. Is there a possibility that could affect the ratings that it gets any, or like if you were to say instead of going with the rows, if you were to go like across the rows at a 45, would that have any effect on how the map may look or come out?
it's a really good question, and so I don't think I've ever seen a paper evaluating that. I'm sure somebody did because it's a very valid question. So I don't know. I cannot answer that from experience, but intuitively, what I would imagine it would be is if you are applying starter fertilizer and you're applying, near the row, near the planting row, with the seed, if you're doing that consecutively for many years, and you're building up, nutrient levels just on the row and not in the in-between row spacing, and your row is always on the same place, that could impact, right? Because, so here, electroconductivity is related to texture, is related to the charges that you have in the soil, is related to the salinity of the soil. So if you think of fertilizer as being a salt, if you are consistently applying a certain type of salt or fertilizer in the same place over and over, and you're not changing that, then you would start just, if we don't even think about the EC map itself, but just thinking from the soil and the fertility side, you would start creating these strips of high concentration of nutrients, and then in the in-between space, low concentration, high, low, right? If that is the case, which I really don't know if it is the case of this field, but if that would be the case, then you would expect to have these strips of high EC, lower EC, high EC, lower EC, that are not related to texture, but are related to this pattern of nutrient application, right? So intuitively, I would expect that that could have an impact on this type of map if that would be the situation. If nutrients are mostly applied in a broadcast way, where they're not being concentrated, but just applied evenly on the soil surface, then this would not be such of an issue, I don't think. Yeah, but that's a really good point.
Thank you for that.
Any other questions here? All right, so I want to invite you to just basically copy the code that we wrote above and paste on the chunk below. because we're really just making one change here, right? So the only change is instead of ECA 30, we want to have ECA 90 on the collar. That's the only thing we're changing. And this would be the deep soil EC map for this field. Right, so as we already mentioned, so the lower values here would probably be associated with sandier parts of the field. The higher values are going to be associated with less sand or maybe more clay parts of the field, if we assume that this data is controlled by texture, which in this case here is a safe assumption for us to do. So I want to ask someone else, you know, if we look at the range of values of the shallow EC going from maybe 0 to, I don't know, 12 perhaps, and we look at the range of the deep one, which is going from 2 to 14. So I guess what I'm trying to get to is that the deep EC seems like it has more values on the higher end of this distribution here than the shallow. How would you interpret that? What does that mean if you look at this and you see this relationship here of higher EC values coming from the deep layer rather than the surface layer? Let me ask Renelisa, what do you think?
So if this is based on the soil texture, I would say that the deeper portion of that area has more clay than the shallow.
Perfect. So Renelisa said here, if we assume that EC is controlled by texture, then that means that our deep depth here is going to have more clay than our top layer, right? Our surface layer. So that's how I would interpret this as well. Yeah. Mm-hmm.
That is why
Was that the question, or do you have a?
question is that is why it is more easy. I mean, there is more clay soil than sand soil.
Okay. So.
Because that is compact.
Yeah, so what Neva was asking is if this field here is tilled, right? So if there is tillage in this field here, that tillage is mostly happening at the shallow surface here, 0.30, and not at the deep surface. So if that has an impact. So I don't think that in itself would have an impact on texture. I mean, of course, like on the top layer, you would be mixing that. So if you have variability in the top layer in texture, that is being homogenized on the top layer, right? You wouldn't necessarily change the texture unless you have very heavy soil erosion. Because when you have, and this is not something that happens, you know, from one year to the next, it's something that probably is going to be multiple years effect of like soil being eroded away, taking with it the clay, and then leaving the sand behind. Of course, this is a process that takes a longer time to happen. But overall, the effect of tillage itself on soil EC, it's probably going to have like a relationship with when tillage happened in relation to when the EC was collected, right? So if you do tillage today and you run a variance tomorrow, I would assume you're going to get different values if compared to if you wait until that soil settles and then you could run a variance after that. It's probably going to change, but at the same time, we're always going to be looking at these maps in a relative way, right? So it would probably be changing the signal of that surface layer and not be changing the signal of the deep layer. But if you're just looking at the surface layer itself, is going to be changing similarly across the field, right? Because you're tilling the whole field. So there is an effect most likely there. But if you are not really looking like, so that we're comparing here deep or shallow and deep, that comparison would be impacted most likely if you till and right away take a various measurement. But if you're just looking at the surface map, that is impacted, but is relatively the same impact, right? That's a good point. All right, great questions. Thanks, everyone. Okay, so again, this is point data. Our goal is to interpolate this, so we actually get a continuous map that then we can overlay with all the previous layers that we've been processing, right? So the next step here is gonna be to interpolate. And if you remember, for us to interpolate, we need to have a grid. Regardless of what interpolation method you're using, you're gonna need a grid to interpolate. And the way that we create a grid is based on our boundary. So the immediate next step then would be for us to bring our boundary here. So let's go ahead and do that. I'm just gonna, so the boundary is a GeoJSON file. So on your system, it's a GeoJSON file. Because we want to import that as an SF object in R, we're gonna use read_SF. So in my computer, if you remember, every time we've been bringing the boundary, you created your boundary on the 05 digitizing project. So if I do .. I get to the main folder of this current project. I do .. again, I see all of my previous projects. And we want to get into the 05 digitizing one. Then in my case, I think that the boundary is on the output folder. So I go to output and then select boundary GeoJSON. If we read that, if you're able to properly navigate to where your boundary was when you digitized, it should come in as a simple feature collection. It should already come with a geodetic CRS, so a geographic WGS84 CRS. Because this, again, is on your file system, it's a GeoJSON file. And when we created it, it had, at that time, a CRS assigned to it. So when we export as GeoJSON, that information goes with it. That's why a CSV file will never have that information as part of it natively. Whereas a GeoJSON file could have, if when you export it, it had that information already. We do want to transform this to UTM as well. So let's do that right here. So after the read_SF, just add a pipe and let's call ST transform. The CRS value here is 6345. So if you run that and you print it, now on your first panel here of the print, it should say projected CRS NAD83 2011 UTM zone 16 north. That's what we need. All right, if you remember here, the way that we create the grid is first giving it or creating the grid as a vector. So in that way, think of each one of the grid cells being a tiny polygon. So we first do that as a vector and then we rasterize it so the grid becomes a raster. And instead of mini polygons, we have raster cells, which are different types of objects. And for us to interpolate, we need to have the grid as a raster. So let's begin here. If you remember, the way that we created the grid was first calling the boundary, right? The boundary is what is setting the extent of the grid. Then we have this function here called st_make_grid, which we're going to use to make the grid. And it has this argument for cell size. We want to say 10. Just to remind you here, this number 10 is going to be in whatever units the CRS of the boundary are. So the boundary right now is in meters. This 10 means 10 meters. So the cells are going to be 10 by 10 meters. If the CRS of boundary were to be WGS84, 10 here would be 10 degrees, which is probably way, way larger than the actual field size is. Another case why it's important for us to have in meters. So if we do that, I'm gonna just go a little bit faster here because we've done this grid a few times already and we walked through each one of the steps in previous classes. So the next step here is gonna be for us to transform this to an SF object. If we just run boundary and st_make_grid, it comes out as a geometry set and not a simple feature. So it's just, a way for us to make this as SF again. So st as SF. We don't need to give any coordinates because it already knows the coordinates. And at this point, this object here is a simple feature again. And as I was telling you, we make the grid as simple feature or as a vector object, but we need to transform it to raster for the IDW function to be able to use it. So let's just give here a pipe and let's use the function st_rasterize. And this function here comes from the stars package. So remember, stars we use for raster object types. The two arguments it has here that we're going to use are dx, so the dimension on the x-axis, I want to say 10, and dy, dimension on the y-axis equals 10 as well, just to match whatever we did initially when we made the grid. And then lastly, we want to crop this raster here to only be within our, well, you know what? Let me just run this and run this plot here below, just so you get a reminder of this. So the way the grid is created when we rasterize it is it has cells everywhere on the bounding box of the field. So meaning that it has cells outside of the boundary as well, but we do not want to interpolate outside of the field. Because this is a raster object now, we cannot just delete the cells outside of the field. We just have to crop it to the field, in which case those cells will become NA. They're still going to be there, but they're not going to have a value, just going to be NA. So we just add a pipe. Let's call the function stCrop and give it the boundary W again. So it crops to the boundary. If we print grid R, now it is a stars object, which is a raster type. And if we just plot it, the shape is not, I mean, it is our field, is just the axes are not properly set, the range of the axis, but we can see now that all the points outside of the boundary, but within the bounding box are now grayed out, meaning they are NA. That's what we need. All right, so for our interpolation step here, we're gonna first do that for the shallow depth in this next chunk. We're going to use the function gstat. If you remember, interpolation happens in two steps, where the first one, we just set the formula in the data set, and then the second one, we actually predict on the grid that we created. So here we have this argument for formula, and I want to say the formula here is going to be, you know what, let me just print our data set that is ECAW, so we can get the column names. So the formula here, I want to interpolate the shallow, so ECA 30 DSM, tilde 1, that's just telling you that you want to interpolate ECA DSM by itself. And then we need to say the data argument, what is the data set name? So data equals ECAW. If you just run that, and then you print ECA 30 IDW mod, you're gonna see that this is just a formula. It's just determining the formula and also the data that the data set where the data is coming from. And now on the next step, we're going to predict, right? So interpolation, 2 steps. We first set the formula with gstat, and then we predict on the second step. So for the predict, if you go to the next chunk, we're going to use the function that's called predict. And we give it 2 arguments. The first one is this object that we just created above with the formula and the data. Give it a comma, and the second argument is the grid. So the grid was saved in this object called grid_R. So if we leave it like that, and now you run it, this is where the actual interpolation happens. And remember, interpolation is just one way of you using a model to make predictions for places where you don't have an observation. That's really what interpolation is doing for us. So now the object here is still a stars object. Now it has 2 columns. One is var1 pred, the other one is var1 var. We already talked about this, that for IDW, we only get a prediction. We don't get a variance or variability measure. You do get the variance here if you do kriging, which is another interpolation method that we're not doing in this class. But if you were to do kriging using some of these similar functions, this var1 var column would be populated with values and not just BNAs like it is now. Okay, so let's just go ahead and create this map here that would be our more publication ready map of the interpolated data. And we're going to assign that to an object called ECA map, so we can call it again in the end of the script. So we're gonna start off with ggplot as always, add a plus. I wanna bring this interpolation map first. So that is gonna be, we're gonna use a geom stars for that because that is a stars object. So geom stars, we're gonna say data equals to the name that we just created above, which is ECA30 underscore IDW underscore Brad. I already want to go ahead and change the color scheme because it's going to be the blue. I want to change that. So I give a plus. I say scale underscore fill underscore Virides C. So C for continuous. This time I want to use continuous. If we just run it at this point and print, this is what our map looks like. So we can see now that we have the cells of this raster here that were interpolated for this map. We're going to do a few customizations here. Well, I guess before doing that, let's bring the boundary. So the boundary as an SF object is going to set the coordinates or the range of this X and Y appropriately. So if just add a plus, the boundary is an SF object. So we use geom underscore SF, data equals boundary W. And I just want to say fill equals NA so we can see through and the boundary doesn't hide the stars behind it. So if we just run that, this is what happens. A few more things I want to do here. The next is just to change the label of the legend. Because this legend here is associated with a fill, right? This is the fill of the stars. We're going to say plus, use the labs function. And here I say fill because again, this legend here is in relation to the fill of the geom. Open close quotation marks. I want to say ECA 0 to 30 centimeters, and then in parentheses, decisiemens per meter. So we get that unit. We just run that, and then you reprint it. This is what we would see. I do want to break line here because it became a little bit too long. So I want to break that line a couple times, one in between ECA and 030. For us to do that, we just add a backward slash n is going to be interpreted as break line. And then I want to add another one after the centimeters. So after centimeter, backward slash n. If you do that and you run it, you're going to see now that you broke line on those points, making our legend text more compact. And then lastly, on this chunk, I want to bring our theme that we created. So just add a plus, and then let's bring my theme underscore map. If we run that and now you print it, this is how the final product is going to look like. And this is what I wanted to have before moving to the next one. So we, let me see here, we're almost at the hour. Yeah, this is probably going to take a little bit more time than 2 minutes. So maybe we can, this is a good stopping point for today. So we basically did the processing, cleaning, interpolation of the first layer, 030. And now then on Monday, we're going to continue and finish the script here, where we're going to do that for the deep depth. And then just finalizing here by making a plot, extracting the values from the raster to vector objects, and then exporting that to file so we can use later. All right, so that was it for today. Let me pull up here and get your attendance. So I will be entering your attendance today for all the classes that happened until now. Just a reminder, if you have missed, you're allowed to miss without being dismissed 5 classes. If you miss more than that, then that could be a problem for you. So let me know if you run into issues that you have to miss. Do let me know before you miss it, because then I can dismiss you from that class and you don't get a missed class in that case. Also on the grades. So right now, I think we're just missing the midterm. to be graded and entered on ELC. The way that I set it up was for you to be able to see up to this point of all the points that you already entered something in and you got a grade for, what is your percent of that, right? Of course, that is not your final grade yet. We still have a few more assignments, quizzes, and then the project that will wait into your final grade as well. But at least of the points that you already submitted for, you're gonna be able to see how you're doing on that aspect. At least I think that's what I hope you can see on your side. At least I can see that on my side. But anyways, again, if you have any questions about your previous grades, if you think you got a grade that does not match your expectation, do let me know. We can talk about it. Sometimes I may make mistakes. I'm always glad to review something and show you, how we got that grade, and go from there. That's all I had. If anyone has any questions, you can ask now. And if not, then I'll see you all Monday. Thanks.